So welcome to part 3 of lecture 7 of Math 2R03. So we just finished proving in the previous part about how we can, given any spanning set, we can remove vectors to get a basis. So we have a large set and we can chop things out. In this part, we want to kind of look in the opposite direction. Okay, so in the opposite direction is we start with a set of vectors that are linearly independent. And what we want to do is be able to keep adding vectors until we get a basis. Okay, so these kind of complement each other. From a spanning set, you can go down to a basis, or you can start with from something that's small, that's linear independent, and expand it to a basis of your vector space. So here's the theorem, which I just denoted as linearly independent sets to basis. And what it says is every linearly independent set of vectors in a finite dimensional vector space can be extended to a basis. So here's how the proof works. Suppose that you have any sort of collection of vectors, u1 through up, be any linear independent set of vectors. And because your vector space is finite dimensional, there are m vectors, probably no relation to the u1 through up that you start with, such that v is equal to the span of v1 through vm. And what you now do is take your initial collection, put them in this order, u1 up to up, and then add the new vectors that span your vector space, v1 through vm. Now, it should not be that hard to convince yourself that this set still spans V. This set spans V. Because once you have a spanning set, anything you add to it will still span the set. But now we have like a spanning set, and the previous theorem says we can chop out or remove vectors. Okay, so if we apply the procedure of the last result to this list, okay, so about kind of looking at each vector sequentially, we get a basis. So we get a basis of V. Okay, so the last result says some subset of this is the basis, but we want U1 through UP to be part of this basis, all right? When you look at how the procedure works though, moreover, no vector UI is deleted because when you do your procedure, you first check you have your U1, and then you check is U2 in the span of the previous vectors, is U3 in the span of the previous vectors. And what we have is when we're doing that procedure, when we do look through the first P vectors, Uj, for example, will not be in the span of the previous guys because these vectors are linearly independent. All right, so for j equaling 2 to p. Okay, so the vectors that we have to remove are the VIs. So we remove from among the VIs. Okay, and so that's how the proof works. So both of these two theorems are excellent results. We kind of use them continuously in linear algebra. We kind of sometimes have we have on our hand a big basis, a spanning set, and we say, okay, let's take the subset that's a basis. This theorem is useful because it says, oh, I have a collection of linear independent vectors, and there's some vectors out there that I can now add to it to expand to a basis for the whole vector space. Let me give you an example of this in practice. Here we have the vector 1, 2 in F2. It's linearly independent. It's a single vector. And we also know that F2 is spanned by the vectors 1, 0 and 0, 1. So the way the proof works up above is to consider this list 1, 2, 1, 0, and 0, 1. Some subset of this has to be a basis for F2. And so we look at kind of how the procedure works is now we have a spanning set and we have to go back to the previous proof, right? So we have, first of all, there's no zero vectors to remove. No zero vectors to remove. So we don't have to worry about that step. Now we look at each vector sequentially, right? And so we have 1, 0 is not in the span 1, 2. So we keep 1, 0 in B. Okay, so now this vector we keep because it's not 0. This vector we keep because it's not in the span of the previous one. What about the next guy? Well, 0, 1 is in the span of 1, 2, 1, 0. And why is that? Maybe you don't see this right away, but it's because since 1/2 times the first vector minus 1/2 times the second vector is equal to 0, 1. So the way that the proof works is we remove 0, 1 from B, and as a conclusion, we get, therefore, the list B 1, 2, 1, 0 is a basis for F2. And we've taken our first linearly independent thing and we've added a new thing to it to make a whole basis for F2. So it's a very handy result. And in the next part of the lecture, we'll kind of see another case where we kind of expand things to a basis and we can then use this to prove results.